So today we're going to talk about experiment 3, which is covering the technique of extraction and recrystallization. We're going to talk about what extraction can do for you, basically. Extraction is a purification technique that uses a specialized piece of glassware known as a separatory funnel. I'm not going to go through how to use a separatory funnel. Your TA will do that for you. But it is a purification technique that allows us to separate components of a complex mixture based on their solubility differences in two solvents. So it does require that we have two solvents. I've drawn here an imaginary beaker, if you will, so just consider this box to be our beaker. We've got a green solvent we're going to call solvent A and a red solvent called solvent B. Notice there's a boundary line between the two. These two solvents are said to be immiscible with one another. Solvent A and solvent B do not mix with one another. Remember your rules from general chemistry and that like dissolves like. And in this particular case, let's say that solvent A is water and solvent B is an organic solvent that is immiscible with water. Okay, so we've got our situation set up here like this. We can have the two solvents that are immiscible, but we can shake these together and make them mix temporarily at least in the separatory funnel and allow things to partition from one solvent into another. And so if we have a compound that likes to dissolve in solvent A, for example, that's where we would find it after the extraction is completed. Likewise, if we had a compound or a component of our extraction mixture that liked solvent B, that's where we would find it afterwards. So let's look at a very simple example to start with. We'll just call this our simple example. And let's suppose we have a mixture that we need to separate that contains sodium chloride and benzophenone. Lone pairs. So both of these are solids, of course. Sodium chloride, just table salt, it's a solid. Benzophenone is an organic molecule, which is also a solid, and you've got a mixture of these two things, and you need to separate them. Somehow the sodium chloride got mixed up with the benzophenone, and you've got to separate them. So how can we do this? Both are solids, but we can separate them based on their solubility differences by extraction. Okay, so let's look at the properties. Sodium chloride, of course, is an ionic compound that when placed in water will completely dissociate into its ions. So it's completely water soluble. Again, those solubility rules that you learned about in general chemistry are going to come back here to help us. Benzophenone, however, draw benzophenone for us, is an organic molecule which is not water soluble. However, it will dissolve in organic solvents, things like methylene chloride or diethyl ether. So it will dissolve in CH2CO2 or ether. And it turns out that water and these organic solvents are not miscible with one another, and so we can use this to our advantage quite easily. So we can take our mixture of our sodium chloride and our benzophenone, we can place it into our separatory funnel, which I'm going to just represent as a box. In that, we have placed water and methylene chloride. We'll use methylene chloride here as our example. And we add our mixture to that, and when we add our mixture to that and shake it up, what we're going to find in the water layer, of course, is the sodium chloride, because like I mentioned here, it dissolves in water forming its ions, so it's nice and water soluble. Sodium chloride does not dissolve in organic solvents. However, the benzophenone will dissolve in the organic layer and is insoluble in the water layer. Given that these solvents don't mix with one another, we can actually remove the water, and we can remove the methylene chloride, evaporate off the solvents, and then we should have relatively pure sodium chloride from the water layer and relatively pure benzophenone from the organic layer. So before we go on too much further into some of this, how would we determine whether or not the top layer was water or the bottom layer was our methylene chloride? If you didn't know, if somebody didn't give this to you, how would you know? You would know this based on density. So you need to look up the densities of the two liquids to determine. And we know that the density of water is approximately 1 gram per milliliter. And we know that methylene chloride is much greater than 1 gram per milliliter. Those are values that you can actually look up. And the most dense liquid will always be on the bottom. Now, if you don't have that information at hand, you can actually put your two solvents together and then add a little bit of water to the mixture and see which layer gets bigger, basically. So what we would do is we would start off with our separatory funnel, put our organic layer in, our water layer, and we would mark the separatory funnel with a line showing where the two layers meet. And then I would take maybe 10, 15 additional milliliters of water, put in there, and what we would notice is that the water layer would actually get bigger in volume and the organic layer would stay the same. And that would tell us which layer is the water layer and which layer is the organic layer. So there are two ways to actually determine which layer is which. Now, this is a very simplified example, and not all examples are quite that straightforward, because it turns out that there are some organic molecules that are soluble in water, and we need to know that beforehand. So let me give you an example of some molecules that are both soluble and insoluble in water that are organic. So the water-soluble compounds we'll list first. This is known as THF, tetrahydrofuran. It is a water-soluble molecule. Another molecule that you're all familiar with is 2-propanol or isopropyl alcohol. This is rubbing alcohol. You buy this as a 70% solution of isopropyl alcohol in water. So it is absolutely miscible with water. And ethanol. Again, perfectly soluble in water. So these are organic molecules that are highly soluble in water, and they're soluble because they meet the 5-carbon rule. They satisfy this so-called 5-carbon rule. And what you do is you look at the number of heteroatoms that have lone pairs of electrons and can form hydrogen bonds with water. And if for each one of these, if there are 5 or fewer carbons, generally the molecule is water soluble. And as we can see here, THF has 4 carbons for this one atom that can form hydrogen bonds. Isopropyl alcohol, of course, has 3 carbon atoms for this one alcohol group, which can form hydrogen bonds. And of course, ethanol has 2 carbons. So all of these molecules satisfy the 5-carbon rule. So now let's look at some insoluble examples, things that you would find in the organic layer and not in the aqueous layer. Ether is an example of this. So this is diethyl ether. We simply call it ether for most practical purposes, but its correct name, of course, is diethyl ether. The molecule that we just talked about, benzophenone, is insoluble in water. And then, of course, alkanes, so 11 carbons, completely water insoluble. Notice ether has an oxygen atom that can form hydrogen bonds with water, and it has 4 carbons just like THF. However, it's not soluble in water, even though it seems to satisfy this 5-carbon rule, and it happens to be insoluble in water due to its shape. So if you'll notice here, tetrahydrofuran is part of a ring, and that gives it an overall dipole towards the oxygen, whereas for ether, the dipole in one direction is canceled by a dipole in the other direction, and so ether is less polar than THF. And since water is a very polar solvent, the polar molecule THF will dissolve in water, whereas the quote-unquote non-polar solvent ether will not. Of course, benzophenone has an oxygen atom which can form hydrogen bonds, but it has 13 carbons, and so it does not satisfy the 5-carbon rule for this one group. And of course, our straight chain hydrocarbon, if you will, has no group that can actually form hydrogen bonds with water, and so it's completely immiscible.